A particle is projected from a point on horizontal ground with an initial speed of 82 meters per second at an angle beta to the horizontal. So here is the initial velocity vector. Its magnitude is 82. Angle is beta. As soon as the particle leaves the launch pad, it follows a parabolic trajectory. So the tangent to the trajectory gives the velocity vector at that point. So the velocity immediately after being launched is tangent to the trajectory. Okay, this is meant to be symmetrical. It's meant to be a parabola because there's no air resistance. So let's get the initial velocity of the particle in terms of I and j. So we have its magnitude and we know something about angle beta. Well, angle beta is fully specified. Tan beta is 40/9. So let's look at the two components of this angle, of this initial velocity vector. I'll show the components in green. So this side is opposite angle beta, so we multiply the hypotenuse, which is 82, by sine of beta. And this component is adjacent to beta, so it's 82 cos beta. So I'm showing the magnitudes of the two components here. As vectors, we need to bring in the unit vectors to fully specify the component vectors of the initial velocity. First of all, let's get sine of beta and cos of beta. Well, we use this information up here. So beta is some acute angle such that when we take the tan of beta, we get 40/9. So you can just draw a rough right angle triangle here, of course. This side opposite beta is meant to be much greater than the adjacent, but anyway. So from this information we can find out what sine of beta is. Sine of beta is the side opposite beta divided by the hypotenuse. So what's the hypotenuse? It's the square root of the sum of the squares, the two short sides. So we get 41, so sine of beta is opposite over hypotenuse. Cos of beta is adjacent over hypotenuse. So now we can write down the component vectors. So this vector has magnitude 82 cos beta, but we multiply it by the unit vector I. The unit vector I, of course, points to the right and has magnitude 1. So if we multiply 82 cos beta by 1, we get a vector of magnitude 82 cos beta, but it's pointing in the I direction. So I'll fully specify those components now by writing I after this. So I'm not just talking about the magnitude, I'm talking about the actual vector when I write in I. And of course similarly j is a unit vector pointing vertically up, magnitude 1, so I'll write j here. So now we have this vector rather than just a magnitude. And of course by the triangle law we add those two vectors to get vector u, the initial velocity. So we multiply 82 by 9/41, that's 2 times 9, which is 18, and we have 82 by 40/41, that's 2 times 40, which is 80. Now immediately after the particle is launched, the only force acting on it is gravity, which is vertically down. So we would have the weight of the particle, which we know as mg. So that force is constant, of course, for objects near the surface of the Earth. So by Newton's second law, the force of gravity it's the only force acting on it, so it's the resultant force is mass times acceleration. So the acceleration due to gravity is g, which for objects near the surface of the Earth is 9.81. So it doesn't matter what the mass is, all objects have acceleration 9.81 meters per second squared vertically down. Okay, so there's no air resistance, so there's no force on the particle in the horizontal direction. The only force on the particle is gravity. So we're only going to look at the y value of this particle. Okay, so we're looking at just the velocity in the y direction, because the velocity in the x direction stays constant. The velocity in the x direction is always 18 meters per second. It doesn't change. It's the velocity in the y direction that changes, because there's an acceleration in the y direction. There's a constant acceleration in the y direction. So we're dealing with linear motion with constant acceleration. But we're talking about the y direction now. So we just want the y components of the velocity vector and the acceleration vector. Well, the acceleration vector is entirely in the y direction. Upwards is going to be positive, downwards will be negative. When the particle reaches its maximum height, its y component of the velocity is 0. Okay, so the x component hasn't changed, it's always 18. So this vector here, when it reaches its maximum height, is actually 18i. Okay, the same as this vector down here. Because there's no air resistance, no force in the horizontal direction. No force means no change in the velocity in the horizontal direction. But we know from a previous video the key point here is when a particle reaches its maximum height, the velocity vector is horizontal. The tangent to the trajectory is horizontal. So the y component is 0. So this is the key point. So we apply this formula to the particle when it's at its maximum height. Vy is 0, uy, and the y component of the initial velocity is 80j. Well, we just want its magnitude. Well, we just dropped the j. Ay, well, the acceleration is entirely in the y direction. It's 9.81, and since it's downwards, put a minus sign. And t then will be the time taken for the particle to get to this position. So all we're looking at here is the vertical component, or the y component of the velocity. So we could just consider this line here, well, it's the y-axis, I'm just showing it down here for convenience. So initially uy, or well, we could say vy is 80. We refer to it as uy for the initial speed. Okay, vy is 80, and you know, as the particle, well, I'm looking at just the projection of the particle onto the y-axis. So the velocity is decreasing because of the minus sign here, and eventually, of course, the projection will stop, and well, we know what time that occurs at. The time is 8 seconds that we just calculated. So now we just want this height. Okay, so I'm just imagining the projection onto the y-axis. All the time, of course, we have the acceleration due to gravity acting, and that's a constant vector. That's not changing. So that's acting to slow the particle down. Eventually it comes to a stop. We want the maximum height. So for linear motion with uniform acceleration, we use this formula here. So we're just dealing with linear motion. If we just imagine the particle projected onto the y-axis, we have the linear motion of the projection of the particle on the y-axis. We can put in a y here to emphasize that we're looking in the y direction. So we just plug in for the time taken to reach the maximum height. The time is 8 seconds. Half of minus 9.81 is minus 4.9. So the maximum height is 320 meters. So that's that height here. So Sy gives us the height of the particle. Okay, it's the displacement in the y direction. So to get the range, we note that the height of the particle just before it strikes the ground here is 0. So we set Sy equal to 0 and we solve. So here's Sy. It's 80 times t minus 4.9 times t squared. We set this equal to 0, and by solving this equation we get the time for the particle to go from here to just before it hits the ground. Time for it to complete the range. Okay, this is a quadratic equation. We factorize t out. The product of these factors is 0. The only way that can happen is if either of them is 0. So if we set this first factor equal to 0, we get the t equals 0 basically, which is at this time Sy is also 0. But that's not what we're after, of course. Okay, the initial time is 0 when the particle is just launched. Its height is 0, of course. But this other time is when the height is also 0. So that's the time taken. That's the time of flight. Notice that we could have got that answer by taking the time to reach the maximum height, which is 8, and multiplying it by 2. Okay, so now we want the range. So that's the distance travelled in the x direction. So here's the formula for distance travelled in a direction along a line where the acceleration is constant. Okay, so it's linear motion with constant acceleration. We're talking about the projection of the particle onto the x-axis. That projection moves at constant acceleration. But what is that acceleration? Well, we know it's 0. Okay, because there's no forces acting on the particle in the x direction. So this term disappears. So all we have to do is multiply the initial speed in the x direction times the time taken. The initial speed is 18, that doesn't change. So multiply speed by time to get distance. And the time is 16. Next we want the 2 times at which the height of the particle is 275. So I'll just mark 275 on this roughly. We know that the maximum height is 320. Okay, so this is the y value. Well, we usually use the letter s to denote displacement, but we could just call it y. So when the particle is at this position and when it's at this position over here, the height is 275 meters. So here's the formula for the distance travelled in the y direction, and we want that distance to be 275. So uy is 80. Half ay we've seen several times is minus 4.9. So we have to solve this quadratic equation for the time. So I get into standard form, 0 on the right hand side. I've divided everything by minus 4.9, so I get roughly this equation here. And we just solve this in the usual way. This equation actually factorizes, but you can use the minus b formula. Set each factor equal to 0, so we get the 2 times at which the height is 275 meters. So obviously this point in the trajectory corresponds to t equals 5, and this one over here must correspond to t equals 11. Notice that we found that at t equals 8 the particle is at its maximum height, and 8 is midway between 5 and 11. So again you can see the symmetry in time as well as in space. A particle is projected from the top of a straight vertical cliff of height 25 meters with velocity 15I plus 20j. So shown are the horizontal and vertical components of the velocity. So we want to just draw this in. We sum these components by completing a parallelogram. Well, it's going to be a rectangle in this case because the components are at right angles to each other, of course. You know, we can draw in the velocity vector. It's tangential to the trajectory. Okay, the velocity at each point of the trajectory is tangential. It's a tangent to it. Okay, it strikes horizontal ground at B, and first we want the maximum time, the time taken to reach the maximum height. Well, we've seen that a few times. When the particle reaches its maximum height, the velocity vector is horizontal, so the j component is 0. So the velocity vector is actually just the horizontal component, which never changes because there's no air resistance. Okay, so it's 15I. I can put in the 0j to emphasize that vertical component is 0. So it's only the vertical component that's changing because the resultant force on the particle is vertically down. So the acceleration of the particle is entirely downwards by Newton's second law. So we're dealing with essentially linear motion with constant or uniform acceleration, but we apply this formula in the y direction. So we want the time, but we know that Vy is 0 when the particle reaches its maximum height. Uy is the initial velocity in the y direction, which is pointing upwards, the positive direction. Ay is vertically down, magnitude 9.81. And t is the time when the the velocity in the y direction is 0, so it's the time for the particle to reach the maximum height. So t is roughly 20 divided by 10, which is 2 seconds. Next we want the maximum height above the ground. Well, we've seen this before. Let's start with getting the maximum height above the horizontal. And then we just have to add 25 on it. So here's the displacement in the y direction, so we can think of our problem as linear motion in the y direction with constant acceleration. So we just fill in for the initial velocity in the y direction, which is 20. Now we're interested in the time when the particle reaches maximum height. Here we'll have minus 4.9. If we approximate 4.9 by 5, we get approximately 20 meters. So we just have to add on the 25 meters. Now, what about the time of flight? Well, in previous videos, the particle was launched over horizontal ground, so we calculated the time taken for the particle to go from here to just before striking the ground again. At this position, we noted that the displacement in the y direction is 0, of course. And we'd solve this equation to find the time of flight. Now, we're not interested in that point, we're interested in this point here. So what's sy for this point? Well, sy can be positive or negative. Sy is actually a vector. You know, when the particle is above the origin, sy is positive. Like this would be sy. The particle is above the origin. But when the particle is below the origin, then this vector is sy. Okay, we'd also show it over here. We could show it over here, of course. We could show the vector anywhere as long as we don't change its direction or magnitude. So this is vector sy. That's going to be a negative vector. So, well, we know what it is actually. We don't have to put a question mark there. We know it's minus 25. Well, we could put in the j if we like, but we normally don't. The sign gives us the direction. There's only two directions to consider for sy, positive or negative. So we know that at this point sy is minus 25. So here's our formula for sy. So we would just set this formula equal to minus 25 and solve. So uy is 20, and of course, as usual, ay is minus 9.81 divided by 2 is minus 4.9, but I'll just round this to minus 5. Okay, it's a quadratic equation, of course. Get it into standard form. I factorized it here. Set each factor equal to 0, so we get t equals 5 or t equals minus 1. Now when the particle was launched, of course, t is 0. And time obviously increases. So this is our answer. At t equals 5, the particle is here. Now what does t equals minus 1 mean? Okay, we normally discard this solution, but I'll just show you what it means. So normally at t equals 0, everything starts, you know, the particle is launched or whatever. But at t, if we could imagine extending time backwards, at t equals minus 1, the particle would be here, where sy is minus 25. So I don't want to dwell too much on this because we normally disregard the solution. Well, we always disregard it. But what it means is that if the particle was launched with a speed and an angle equal to the velocity at which the particle strikes the ground at b, okay, so the velocity at which is just immediately before it strikes the ground, the velocity would be tangential to the trajectory, so it would look like this. Well, these two vectors would have the same magnitude. So next we want the distance from A to B. Now we know the time of flight. We also know that the horizontal component of the velocity never changes. So this is ux, because there's no force in the horizontal direction. So in each second the particle travels a horizontal distance of 15 meters. So in 5 seconds it will travel a horizontal distance of 5 times 15 or 75 meters. So more formally, the distance in the x direction of course is given by this formula here. This is for linear motion with constant acceleration, but the acceleration is 0 since the force in the horizontal direction is 0. The force is 0 in a particular direction. If the resultant force is 0 in a particular direction, then by Newton's second law the acceleration is 0 in that direction by F equals ma. So you can see it from this too. Ux is 15 and the time of flight is 5. Finally, we want the speed of the particle just before it strikes the ground. Well, we're dealing in each direction, the y direction or the x direction, we're dealing with linear motion with constant or uniform acceleration. So let's look at the y direction to get the y component of the velocity immediately before the particle strikes the ground. Well, the time is 5, so we plug 5 in for t. Now the y velocity initially is 20 meters per second. The acceleration is pointing downwards, it's minus 9.81, and the time is 5 seconds. Now I'll round 9.81 to 10, so we have 20 minus 50, which is minus 30 meters per second. So the minus sign of course makes sense, because the y component of the velocity just before it strikes the ground is pointing downwards in the negative direction. Now what about the x component? Well, that's pointing in the positive direction, and we know that doesn't change. The x component is 15 meters per second. We can see it from here, of course. Vx equals ux plus ax times t. Ax is 0, so it doesn't matter about the time. Vx is equal to ux, which is 15 meters per second. And that's positive, so it's a vector pointing to the right. So anyway, everything makes sense here, of course. Okay, I've written them in the magnitudes of these two vectors, so I don't have a minus 30 here because I'm just looking at the magnitude. These two vectors and the blue vector, the resultant, form a right angle triangle, of course. So the speed is the magnitude of the final velocity. Well, we can actually write down the final velocity vector. Okay, I'll write it down as a vector first. And so I'll use the unit vectors I and j. So this is the horizontal vector, it's pointing to the right, 15i. This one is minus 30j. So if we call the final velocity v, it's going to be 15i minus 30j. So what's its magnitude? Its magnitude is its speed. So we can write the magnitude like this, or just drop the arrow, and we just use Pythagoras. Now of course you can write this as a decimal if you want to. Alright, so the units are meters per second, so that's the magnitude of this vector. Now, suppose that we wanted to go further and get the angle of impact. Well, we could denote this angle as the angle of impact, which is the same as this angle in here. Okay, see, this final velocity vector v is tangent to the trajectory, so the angle between the trajectory and the horizontal just before impact is the same as the angle inside this right angle triangle. But what is that angle? Well, it's inverse tan opposite over adjacent, or inverse tan opposite, or inverse sine opposite over hypotenuse. So the angle of impact is inverse tan 30 over 15.